Okay, this is part 4 of the counting example problem videos. So in each part, the problems have gotten a little more difficult. So at this point, we're at the more advanced level of counting problems, which means that not only will these problems in general require you to understand the basic fundamental counting methods, the permutations, combinations, repeated, non-repeated, indistinguishable elements, some real product rule, all of that mixed in, but also potentially events within the problem that have overlapping outcomes. So we'll need to use the principle of inclusion, exclusion, the Venn diagrams. Or these problems could just require you to break everything up into 4 separate pieces and calculate the counts and then just sum all of those pieces. It's just a big OR problem. You have to solve for, okay, it's this case or this case or this case or this case and sum everything up. Okay, this first problem does a good job of illustrating how for any general counting problem, you really want to make sure you carefully understand exactly what the problem is saying, because otherwise you can fall into a trap of making a quick assumption about the type of counting category the problem applies to. Okay, so it says, how many ways are there to distribute 5 balls into 7 boxes if each box must have at most 1 ball in it if both the balls in the boxes are labeled, the balls are labeled but the boxes are unlabeled, the balls are unlabeled but the boxes are labeled, both the balls in the boxes are unlabeled? Okay, so one of the big factors here is that each box can have at most 1 ball. Okay, so we need to keep that in mind. That's a big restriction. Okay, now let's start with part D. So, all right, well, we've got these 7 boxes. Okay, they're unlabeled for this problem, and 5 balls that are also unlabeled for this particular problem. Okay, so it's easy to go straight into, all right, we can do, 5 slots for 5 balls. We're picking from 7 boxes, right? So, okay, yeah, we got these 5 balls here, and we're going to assign to each box, but the order doesn't matter because the boxes there, it's indistinguishable boxes and balls as well. So we've got 7 boxes. Right? 5 balls. Now they're unlabeled, but we're just putting these labels just to keep our thoughts organized. This is like the first ball we pick, the second ball we pick, the third ball we pick. But order doesn't matter, right? So it's a combinations with repetition problem, and that's it, right? We're choosing from, let's see, 7 boxes for 5 slots. There you go. 7 plus 5 is 12, minus 1 is 11. 11, choose 5. Okay, but again, you really need to be careful and take it slow so that you understand exactly what kind of problem you're dealing with. Okay, because first of all, doing it that way, the first thing that comes to mind is what we counted there was we could have all of these be box A, or all of these be box B, all of these be box C. Well, each box can have at most 1 ball in it. Okay, but another issue, even if there wasn't a restriction of each box having at most 1 ball, this would still be a problem because having all 5 balls in box A is the same thing as having all 5 balls in box B, all 5 balls in box C. It's the boxes and the balls are unlabeled. It's more about are all the balls in one box and all the other boxes have no balls? That's one configuration, right? But we can't even do that because we have the restriction that each box has at most 1 ball. So what we really have here, the problem is this. So yes, we can put 5 slots here for 5 balls, and even though the balls are unlabeled, we can still put these labels just to organize our thoughts because there is 5 separate indistinguishable balls. And this is like the first ball we choose, the second ball we choose, the third ball we choose. So just for the sake of organization, we can label these here. But really what we have, because the boxes are indistinguishable, and because each box can have at most one ball, then what we're really doing is we can just put the letter B here and say this is a box, right? But we know that this doesn't mean that if I do all B's, then we're putting all the balls into the same box. This is just each letter. Like, okay, we could start with this. Each letter is going to be one box. Let's start here. 1, 2, 3, 4, 5, 6, 7. Each letter is one box, right? And you can only use one letter. Like there's no repetition here. Once you choose an A, you're done because each box can have one ball in it, right? You could do A, F, G, C, B. You can use. You can't. There's no repetition, right? And order doesn't matter. So maybe this is okay. 7, choose 5. Well, no, we can't do 7, choose 5 because if we did that, then that's implying that if you put ball 2 in box F, that would be here, and you put ball 4 in box C, then we're counting if you switch those two balls. We don't want to count that. So really, it's we have to just redefine this. We can model this as we'll just put B here for this is just box, right? This is a ball in a box, one box. This is if we're going to model this is a combinations with repetition problem. We can choose B as many times as we want because there's really 7 B's but only 5 slots, right? It's a combinations with repetitions problem where we've got 5 slots and we can choose from. We have one thing to choose from. But like the way it's defined is ball 1 is going to go into a single box. Ball 2 is going to go into another box. Ball 3 is going to go into another box. Ball 4 into another box. Ball 5 into another box. That's it. So we're choosing from 5 items, combinations with repetition. 5 plus 1 is 6, minus 1 is 5. One outcome. There's only one way. There's only one outcome. You're going to have 5 boxes with 1 ball and two empty. There's only one outcome here. Okay, what if the balls are unlabeled, but the boxes are labeled? So in that case, we have 3, 4, 5. So we can label the balls just for the sake of, okay, we're picking up ball 1 and doing something with it, and then picking up ball 2. But they're really indistinguishable. Okay, but now the boxes are labeled. Okay, so this is going to be it's not repetition because we can still only use, we can pick a letter and we're done with it because of this at most 1 ball. Okay, but what we're doing is the count is going to be 7, choose 5. Because if we did A, C, D, G, B, right? Ball 1 went into box A, ball 2 into box C, ball 3 into box D, 4 into G, 5 into B. We don't care if we reorder these letters. If we scrambled these same letters here, that's the same thing. The balls, because the balls are unlabeled, and these are the same boxes. Okay, we don't care if ball 2 goes into box A and ball 1 into box C. That's the same thing. The balls are indistinguishable. But we do care if we switch out D with E because the boxes are labeled. Because in that case, you're saying, okay, I'm taking this ball from box D and putting it in making that empty and putting it in box E. So that's 7, choose 5. Okay. Now, what if the balls are labeled, but the boxes are unlabeled? So the balls now. This is tricky. Well, okay, what we've got here is we've got 1, 2, 3, 4, 5, 6, 7. We'll make the boxes the slots. Okay, so we've sort of numbered the boxes in the sense that This is the box that's all the way to the left. The box is all the way to the right, but they really have no label. All right, so now what we've got then is, to choose from, we've got 1, 2, 3, 4, 5, and then 2 zeros is what we've got. It means there's no balls in the box. We only have 2 to choose from. But these are not repeated, right? You can only use them once. So, okay, we've got 7 items to choose from for 7 slots, but the order doesn't matter. The boxes are unlabeled. If we do 0, 4, 2, 0, 3, 1, 5, right? We've chosen all the items. We have 2 boxes that are empty, but we don't want to count rearrangements. The boxes are unlabeled. So it's just 7, choose 7. It's 1 again. Okay. Now, what if both the balls and the boxes are labeled? So okay, well, in that case, we can think about how we've got these 5 balls, these 7 boxes. So, and now we're picking 7, we're picking 5 from 7, but the order matters, right? So this is just going to be 7P5. But there's no repetition because of the at most 1 ball. We can't pick box A twice because each box can have at most 1 ball in it. How many ways can a book distributor pack 5 copies of a book into 3 identical boxes? Okay, so this is going to be a good example of how we won't actually be able to put this problem into a specific category. So does that mean we can't solve it? Well, we're going to be able to solve this by just doing a manual count. But let's say you had a bigger problem with bigger numbers where you couldn't do a manual count. Well, then what you would do is you'd have plenty of time. It's like you're doing this for your job or something, so you'd have time to think about it. But you would just solve this problem with smaller numbers like these for a few different cases and figure out what the pattern is, and then come up with your own formula. So, okay, but how could this not fall into a specific category? Well, okay, let's take a look. So you've got, let's see, we've got these 3 identical boxes. Okay, now we're picking from 5 books to put into the boxes. Okay, so we start off with what we know. I mean, we could, this with combinations with repetition is nice because it doesn't take order into account. And so, okay, we can, let's see, 1, 2, 3, 4, 5. So we can label these as the books, but this is just the first book we picked, the second book we picked. The books are indistinguishable, right? It's the same book. Okay, now this is a little bit different than the previous problem because we can't just say, okay, we're just going to put, since we don't want to label the boxes, we're just going to put 1 letter. The problem with that is we don't have the restriction in the previous problem where each box can only have 1 book. Otherwise, this would be fine. Well, it kind of wouldn't work out in this case because we've got less boxes than books. In the previous problem, we had more balls than bins. But regardless, we can't really do that because we could put all 5 books in a single box. Okay, so we can go ahead and just to get something going here, let's put labels on the boxes. Okay, and then we'll try and see if we can maybe use the division rule or something in a simple way. So, okay, the best we can do here as far as trying to take into account that everything's indistinguishable, there's no, order doesn't matter, etc., is we can do some sort of a combination, but do we want to do with repetition or without repetition? Well, we want to do with repetition because we could make all of these A, right? That is an option here. Right? We could put all five books into box A. So, all right, so we can start by saying that for combinations with repetition, we're choosing from a group of, wait, hold on. Yeah, this should be 3 boxes here. So A, B, C. We're choosing from a group of 3. A group of 3, we're choosing 5 with repetition. So 5 plus 3 is 8, minus 1 is 7. So 7, choose 5. Okay. But we know that this number is going to be too big because we don't want to. Included within this count is all the 5 books go into box A, all 5 books go into box B, all 5 books go into box C, but that's the same count. The books and the boxes are indistinguishable. This is just saying, okay, we put all 5 books into one box. That's one outcome, not 3. Okay, so maybe we're just triple counting then. Maybe this is just triple counting. So if we just divide this by 3, we've got our count. And for some circumstances, that might be right. What you would need to do is, if you had, okay, how many ways can the distributor do 10,000 books into 500 boxes, something like that, right? What you would do in that case, if you couldn't use one of the basic methods to figure it out, right? So if you kind of laid it out like this and you realized, okay, maybe I could divide by 3, but I don't know for sure. You know, we can't. That might be true. But you can't say it for sure. Then what you would do is you would come to a smaller problem like this, and maybe you would start with 4 books going into 2 boxes, or it would be or 3 books going into 2 boxes. And if that worked, you want, if let's say 3 books going into 2 boxes worked, well, you wouldn't want to stop there. You'd want to check, okay, what about 5 into 3? What about 7 into 5? You just want to check it out. Okay, and then once you see a pattern, then you could make a formula and apply it to the big numbers. Because, okay, if let's say we looked here, and okay, so are we just triple counting? So here's the cases where you have all the same letter. What about when you have, this is, wait, 1, 2, 3, 4. So we need an extra letter here. Okay, what about the cases where you have 4 books in the same box and 1 book in another box? So you could put all the 4 books in the box A, 4 books in the box B, 4 books in the box C, and then, okay, but you could also do this and do this and do this, right? Each of these, we've got 4 books in one box and 1 book in another box. So no, we can't just divide by 3. There's 6 outcomes here. Dividing by 3 would only work if for all of the cases of, okay, 5, if we saw for each of the types of cases where you have, like, you know, a certain number of books in one box and a certain number in the other boxes, it's always triple counted. Well, here it's triple counted here, but not here. So we'd have to do a whole investigation. Do this for, you know, you want to do it for a few cases, probably 3 or 4 cases, you know, 3 books into 2 boxes. If that works, well, don't stop there. Check 5 into 3, then maybe check 7 into 5. Then check maybe 7 into 3, right? Just check it for a few cases, make sure it all works, and get a formula. Okay, but now if we do this manually, we can see that, let's see. So if we just divided this by 3, what would we get? So 7 factorial over 5 factorial times 2 factorial times 3. So that's 7 times 6 over 2 times 3. So we get 7. Okay? Let's see what the actual answer is. So you could do, it's 5, 0, 0, 5 books in one box, none in the others. You could do 4, 1, 0. You could do 3, 1, 1. You could do 2, 2, 1. Okay, you could do not 1, 3, 1, 2, 1, 2. No, that's the same as this. 2, 2, 1, 1. No. Oh, yeah, 320. So there's 5 cases, not 7. Okay. You decide to give away your video game collection so as to better spend your time studying advanced mathematics. How many ways can you do this, provided you want to distribute your 3 different PS4 games among 5 friends so that no friend gets more than 1 game? Okay, so for this first case, we've got these 3 indistinguishable objects and these 5 friends that are kind of indistinguishable as well. But there's no repetition here because you can't just you can't just keep picking games and friends or anything. So what we've got is these 3 games, let's say, and these 5 friends. So friend A, B, C, D, E, and these 3 games here, game 1, game 2, game 3. And so you could do, okay, I mean, I guess they're not indistinguishable maybe. Because you could give friend 1 game 1. You could do this, but then another way you could do it is give your friend B game 1. So, okay, maybe the order matters. So, okay, in that case, it would be 5P3. Okay, case 2, you want to distribute your 8 different 3DS games among 5 friends. So, okay, this is a little bit different. We can't just say 8P5 because it's like we had 5 friends. That if we just use what we did here, it would be something like 5P8, which doesn't make sense, right? Because this is the number of friends. So, all right. What do we have here? Can we say that we've got the 5 friends and the 8 games, the 8 games and the 5 friends? Would that work? So a friend's going to have more than 1 game if you're going to distribute these 8 games to 5 friends. So you could give all 8 games to friend A, all 8 games to friend B. So this is a repetition problem, but is it combinations or permutations? Well, it's permutations because we said order matters. Like if this is game 3 and game 4, well, if we give friend A game 3 and friend B game 4, we want to count the ordering. So, okay, permutations with repetition is just that's easy. It's 5 to the, we're choosing from 5. There's 8 outcomes, so 5 to the 8. All right, case 3, you want to distribute your 8 different SNES, I guess that's Super Nintendo, games among 5 friends so that each friend gets at least 1 game. All right, so we can't do 5 to the 8th in this case because with 5 to the 8th, that's counting if 1 friend got all 5 games. In which case, right, that wouldn't fall under the category of each friend getting 1 game. So we could think about if we started with 5 to the 8th and then subtracted out the opposite of this. So we subtract out so if each friend gets at least 1 game, then the opposite is that you have at least 1 friend that didn't get a game. Okay, now in relation to this 1, 2, 3, 4, 5, 6, 7, 8, what's the requirements for that? C, D, E. In order for that to happen, so you've got, you just don't have one of the letters in here. So we could say that you could have, what would that be? 4 to the 8th would be the case, one case where, let's say you have friend E doesn't get a game. Then what's the total number of outcomes where you're just distributing 8 games to 4 friends? It's 4 to the 8th, right? You could give all 8 games to friend A, all 8 games to friend B, whatever. Okay, now, but it's 4 to the 8th outcomes that don't include E, where E didn't get a game. But there's the other case where C didn't get a game, and you have another 4 to the 8th outcomes. So it's 5 times 4 to the 8th. Is that all the cases where you have at least one friend that didn't get a game? No, because you then could have, you've got 5 to the 8th minus 5 times 4 to the 8th. But then you could have a case where where D and E don't get a game. In that case, it's 3 to the 8th. Okay, but now what do we want to multiply 3 to the 8th by? It would be what? 5 choose 2. For this case, it was 5 choose 1, because you have from 5, you choose one person who's not going to get a game. Here it's 5 choose 2. Okay, now let's see. We've got next it's 5 choose 3 and then 2 to the 8th. Then next it's 5 choose 4 and then 1 to the 8th. And then we need to go one more? Or I don't think that's going to work. Because that would be the case where all 5 don't get a game, and then that doesn't make sense. This is counting here. 5 choose 4 is what? 5. So this is 5 choose 4 times 1 to the 8th is 5. That's counting the case where you give all 5 to friend, or all 8 games to friend A, all 8 games to friend B, all 8 games to friend C, all 8 to D, all 8 to E. It's counting those 5 cases because 4 friends didn't get a game. So, but there's no 5 friends don't get a game, because then you don't distribute any games. So this is it. This is the answer. The dollar menu at your favorite tax-free fast food restaurant has 7 items. You have $15 to spend. How many different meals can you buy if you spend all your money and, purchase at least one of each item? All right, so it's tax-free, so it's just like everything's $1. And there's 7 items. And so, we can either treat we're picking from the dollars and these items are the slots, or vice versa. So how do we want to do this? Well, we can pick the same item more than once. So maybe we want to say we have repetition here. We could pick the same item more than once, and we've got these 15 slots. Okay, so would that work? Or maybe we want to switch it. So we've got to purchase at least one of each item. Okay, and then I'm assuming order is not going to matter here. So in that case, it's like if there's 7 items, you've got A, B, C, D, E, F, G. Order doesn't matter. So like this is one configuration here. But you can mix these all in, it doesn't matter. And what we're left with is we've got 8 slots with 7 items, right? We're counting, this is what we're counting. This is what we're counting, because once we get the total number of outcomes here, well, then you're just throwing this in. Like, it's like if we did this count and we got all these different snapshots of these events, right? However many events there are. Well, then to get the reality of the situation, you just go to each item, and just put one more. It's the same number of snapshots. So, that is then you've got, this is combinations, because the order doesn't matter, with repetition. So you're choosing from 7 items for 8 slots, combination with repetition. So 8 plus 7 is 15, minus 1 is 14, so 14 choose 8. Okay, now it says you can possibly skip some items. Possibly skip some items. Well, let me leave this. Okay, so what does that mean? Well, we could already possibly skip some items. Like with combinations with repetition, you could choose all item A, right, for all 15 of these slots for each dollar. We don't have to choose at least one. This is a new criteria. So, yeah, I mean, this just a combinations with repetition accounts for that. You could skip items. So, okay, you're choosing from 7. There's 15 slots. 15 plus 7 is 22. Minus 1 is 21. So 21, choose 15. Okay, now last is you don't get more than 2 of any particular item. Okay, now in that case, we've got to use, like, break this down into some OR problems. So, or actually, no, we might want to model this differently. In that case, we would say that this is 14 items, but it's not repetition, right? You got 2 A's, 2 B's, 2 C's, and when you choose one, it's not, it goes away. Now, but how would that work out? So if you had like A, B, C, D, right? So you could choose an A here, an A here, well, wait. You can't do this because if you spin, there's no outcomes here. It's a trick question because you can't. How are you if you're going to spend all $15? Yeah, you spend all your money. Then you're going to have to buy it's like a pigeonhole problem, right? You're going to have to buy one item 3 times. You have to. So, okay, there's no ways to do that. How many ways are there to distribute 5-card poker hands from 52 cards to each of 3 players? Okay, so you have a 52-card deck, and so you give one player a 5-card hand, then you give the next player a 5-card hand, then you give the next player a 5-card hand. Okay, so the order doesn't matter. So you're going to start with 52, choose 5, right? That's the number of outcomes for the first player. And that's our first event, right? It's like this is an event diagram, and you've got these 3, we're going to have 3 events with number of outcomes M, N, P. And now, but are they overlapping? They kind of are because we're pulling from the same, for each of these, we're pulling from the same deck. So we have to think about that. It's hard to really model this with an event diagram because we're pulling from the same group for all of these. So we have to, that's something to consider. So, okay, so yeah, I mean, I'll put that here. 1, 2, 3, 4, 5, and then, okay, so now here we've got 47 cards left. So you have 47, choose 5, and then here you've got 42, choose 5. Now we just need to think about the fact that we're, for all of these, like this group here is dependent on this group. This group here is dependent on this group. So you have to think about that. If that's something that's going to come into play with your problem. But it's probably not here because we're dealing with combinations. We don't care if the, well, because like this could be, you could have, okay, Jack of Hearts, 3 of clubs, 4 of spades, 5 of spades, Queen of diamonds. Then this is a 7 of clubs, 5 of clubs, Jack of hearts, 4 of spades, Ace of diamonds, right? But because we're pulling from the same group, this could have been a 7 of clubs, right? These groups aren't independent. They're connected from the same standpoint that we're pulling from the same group, right? Like this hand here could have been this hand here, and vice versa. You might say, well, why is it vice versa? because here we're only pulling from 47 cards, because if it's still the same thing, like if this hand was this hand, let's say we switch these two. Well, okay, here's the first hand, you're left with 47 cards, right? So, okay, how does that come into play here? Well, if we multiply these, that should just account for everything. We should be good. Because, okay, order doesn't matter within the hand itself, right? Order doesn't matter. We don't care if the 3 of clubs and the 4 of spades switch spots. We don't care. We've accounted for that with the choose. Okay, but when you multiply these, and since we're choosing from the same group, it is counting the fact that, okay, you could have had a 7 of clubs here and the jack of hearts here. That's why it's 52. So, okay, yeah, this should be fine. It's 52 choose 5 times 47 choose 5 times 42 choose 5. After a late night of math studying, you and your friends decide to go to your favorite tax-free fast food Mexican restaurant, Burrito Chime. You decide to order off the dollar menu, which has 7 items. Your group has $20 to spend and will spend all of it. So it's the dollar menu and tax-free. And we're going to spend all $20. How many different orders are possible? The order in which the order is placed does not matter, just which and how many of each item that is ordered. Okay. So we can lay out the dollars as the slots and the items as the orders, or as the objects. 7. Okay, so we could order 20 of item A or 20 of item B, but the order doesn't matter. The order in which the items, like which one you order first and whatnot. So this is just going to be combinations with repetition. We're choosing from 7 objects. There's 20 slots. So 20 plus 7 is 27 minus 1 is 26. 26 choose 20. How many different orders are possible if you want to get at least one of each item? Okay, so we can bring this back. So if you've got at least one of each item, then what you're doing in that case is you've got, it's like we started off with this 20 slots, but now we can assume that 7 slots are taken up already because we're getting one of each item. And now what's remaining is 13 slots, which we can get whatever we want. And so we're just going to count, the combinations of repetition, we're just going to count you're choosing from 7 for 13 slots. Because once we get this count, 13 plus 7 is 20, minus 1 is 19. Once we get this count, you might say, well, what about the other 7? Well, you just throw them in there into those snapshots, right? You're going to have this many snapshots. 19, choose 13. You can have this many snapshots. Well, you're going to take those original 7 items and just mix them into those snapshots, those pictures. All right, how many different orders are possible if you don't get more than 4 of any one item? Okay, so we can try and think about this from the perspective of trying to subtract out what we don't need. So we've got 26 choose 20 possibilities, but those include when you get more than 4 items. So we can solve for, though, we just did a problem where we solved for the total number of orders possible if you get at least one of each item. Well, what if we solved for the total number of orders possible if you get at least 5 of each item? Okay, well, that's a start, but the problem is that it doesn't include that, okay, you got 5 of just one item, and you didn't get 5 of any of the other items. We don't want to include that either. So, okay, let's try and look at this more officially. So, okay, we've got the count of all the possible orders. And so what are the sets here? If we're trying to subtract something out, right? Here's the system. We're trying to subtract something out. from the system. What are the sets we're trying to subtract out? We're trying to subtract out all of the possibilities, the outcomes where at least just one item was ordered 5 or more times, right? But there's 7 of those sets because there's 7 items, and they're all potentially overlapping. Maybe none of them are overlapping. We can assume, but we can just with anytime we do this, we can just assume they're overlapping and then figure it out as we go. So, okay, what we've got is we're trying to figure out. We want to get A union B union C union D union E union F union G, where it's each. This is each item. The outcomes contained within these sets is the number of outcomes or the outcomes where you ordered item A 5 or more times, item B 5 or more times, item D 5 or more times. You combine them all together and remove the duplicates. If we could get this, then we just subtract that from 26, choose 20, and we've got it. Okay, so we can start with how many items are in just A and B and C and D and E and F and G. It's going to be the same, right? The total outcomes where it was, you have at least 5 of item A was ordered. Okay, well, in that case, you've got 5 slots filled up. And so you're just choosing from, so, okay, it turns into combinations with repetition because you could start with 5 of A and then order the rest as A, right? It's as long as you've got at least 5 of A, then it's, let's see, it would be, you're choosing from 7 items for 15 slots, combinations with repetition. So 15 plus 7 is 22. That's 21, choose 15, right? But we've got 7 of these. So 7 times 21, choose 15. Okay, now we want to subtract out all of the intersecting pairs here. But how many of those are there going to be? How many? So it's subtract out the number of elements in A intersection B, A intersection C, A intersection D, etc., all the way down the line. So we know there's going to be 7, choose 2 of these. So 7 factorial over 5 factorial times 2 factorial. That's 7 times 6 over 2. So there's 21 of these. So 21 times, okay, A intersection B. How many are in A intersection B? So you have at least 5 of A was ordered and at least 5 of B were ordered. So that means 10 items are taken up. You're left with just 10. So you're choosing from 7 for 10 slots. So that's 10 plus 7 is 17. 16, choose 10. Okay, now we want to add the intersection of 3 of these. So like A intersection B intersection C, A intersection C intersection D, etc. So how many of these are there going to be? Well, 6, choose 3. So that's 6 times 5 times 4 over 3 times 2. So there's 20 of these. Okay. A intersection B intersection C. At least 5 items were 5 were ordered for each item. So there's 15 slots taken up. So we're just left with 5 slots. So 7 plus 5 is 12, minus 1 is 11. 11, choose 5. Okay. Now what about the groups of 4? So like A intersection B intersection C intersection D. So in that case, we've got, how many of these are there going to be? It's 7, choose 4. So that's 7 times 6 times 5 over 3 times 2. 7 times 5 is 35. So 35. So, okay, A intersection B intersection C intersection D. You've got each of those items is ordered at least 5 times. So that takes up 20 slots. It takes up all the slots. So it's really 7. You're picking from 7, choosing 0. 7 plus 0 is 0, minus 1 is 6. So 6 factorial over, it's just 1. Right? There's only one outcome there. There's only there's only one outcome if you're forced to order at least 5 of 4 items, right? Okay, but now if we kept going, they're all going to be 0. There's no intersections of 5 and whatnot. You can't order. You only have $20, right? So this is it. So we've got, let's see, 7 times 21, choose 15, minus 21 times 16, choose 10, plus 20 times 11, choose 5, minus 35. So did I get that right? Let's see. 7 times 21, choose 15, minus 21 times 16, choose 10, plus 20 times 11, choose 5, minus 35 is 220,885. Okay, so now we just take 26, choose 20, and subtract this. So 9,345. There we go.